All right, so today we're going to pick it up where we left off last time. We are currently looking at the slides in Brightspace that are called Preview of Calculus. Okay, so in other words, this is material that we likely saw in pre-calculus, but we need to review it in order to make sure that we understand what we're doing when we start the real new content in Chapter 1. So we left it off with a discussion about graphs. By the way, I did introduce something new into the folder here. I have this chart that is actually, I find to be quite useful when dealing with trig problems, and we will be doing that in a little bit. Part 4 of these this preview chapter does discuss trigonometry. So what you're seeing here is a chart that gives us some of the standard angles, and it's listed in both degrees and in radians, which is kind of nice. So we'll get back to this when we're ready for it, but it is now posted in Brightspace in case you want to use it when you're working on your assignments. Anyway, so where did we leave off? Let's take a look at our slides. We're going to be reviewing graphs, and you'll see that, of course, we've seen many graphs. Here they're pointing out to us that that point that they've chosen, x comma f of x, shows us that the x-coordinate gives us the horizontal distance from the origin, and the f of x is the height from the x-axis. Okay, so this is how graphs work. Now, just because we have a graph doesn't guarantee that, though, this is a function. So we have to remind ourselves that all sets of ordered pairs that we could come up with can be thought of as a relation, but a function requires every element in the domain, in other words, the x elements, to be associated with exactly one element in the range, which are the y elements. So you may have seen these types of diagrams before, where we've got the domain could be represented as a set. And let's just say, let's keep it simple. Say x only contains the integers 1, 2, and 3, and y contains, let's say, 3, 6, and 9. So let's assume that x equals 1 is associated with y equals 3, x equals 2 is associated with y equals 6, and x equals 3 is associated with y equals 9. So you can see this one clearly is a function because every one of these x's is associated with exactly one of the y's. Okay, remember this set is known as the domain. This is the range. And this f of x is the function that's connecting x with y. Okay, so every x gets assigned to a unique value y, and that's it. It's a function. If not, it still counts as a relation. Right? So in other words, if you had something like this, what if instead I had something like this? So this one doesn't qualify as a function because x equals 3 is not associated with any of the elements of x, of y rather. So even though it's not a function, it still is referred to as a relation. So you can think of a function as a special type of relation. Now, in order to tell just by looking at a graph if we have a relation or a function, there's a very simple test, which I believe we talked about last time, called the vertical line test. And so the way it works is this. With the vertical line test, you very simply draw a line through your graph. To mention it here, vertical line test can be used to determine if a graph represents a function or a relation. Okay. So if a vertical line crosses the graph more than once, then the graph represents a relation, but not a function. Okay, so it's very simple. Um, Make that a little bigger so you can see it. So here, for example, they're pointing out that this one right here is not a function because this red line, the vertical line, cuts through that curve at two different points. And so you've got these two, the x is associated with two different values of y. That's what the problem is. The one in this middle is a function. It's a strange function, but it is a function because no matter where you put that vertical line, it'll never cross through that graph more than once. The one on the far right, in spite of the way it appears, is also a function. Okay, it's a discontinuous function, but it's still a function. And that's again because no matter where you put that vertical line, you'll see that it will never cross the graph at two different points. Okay, so visually you can see just by looking at it if it's a graph, if it's a function or not. And then we've got some basic examples here. For example, the one on the far left is clearly a linear function. Specifically, it's called the identity function because if you notice, no matter what x is, y has the same value. We call that the identity function. It has a slope of 1 and an intercept of 0. Here is a parabola, and it is f of x equals x squared. And that means that it starts here at the origin. And then you can see that it will never have any negative values. This last one is the cubic function because it is x cubed. And if you notice in all three cases, if we were to try the vertical line test, it would pass because the vertical line will never cut through any of these more than once. Now, also after a while, you'll start getting used to the way these functions look. For example, the one in the middle is a quadratic function. The one on the far right is a cubic function, and you'll start to get familiar with the way they tend to look. They have similar shapes. For example, the one on the far right, the curvature is unique to a cubic function. And so anyway, down here we have some more key cases. The one on the far left is the square root function. You notice how it starts at the origin, and then it increases relatively slowly. The one in the middle is our old friend, the absolute value function, and it is two straight lines. This is the line y equals x. This is the line y equals negative x. And are joined here at the origin. Because they come together at a sharp point like that, this is often called a piecewise function. Because what you effectively have done is put together two separate functions and created a new one as a result. So that's why it's sometimes called a piecewise function because the behavior is very different when x is below 0 and when it's above 0. And this last one is the inverse function, or sometimes it's called the rational reciprocal function. This is f of x equals 1 over x. You notice there's an asymptote here in the center. The function itself can never quite reach that vertical axis. There's no value of x at which y could be 0. Okay, so again, there's a discontinuity here. And that vertical line is called an asymptote. And that simply means that the function converges towards it, but never quite reaches it. Okay, so these are also functions. And again, if you tried the vertical line test here, you'd see that it would pass in all three cases. Now, this is something that you don't always have time to do in pre-calculus. These are transformations. What they want you to do is see how small changes to these functions will affect the graphs. Okay, so for example, if you notice here, I have two parabolas. Hold on one second. See if I can make this a little bigger. Oh, okay. It's no, this is very weird. There we go. I don't know what that was all about. Um, I was hoping to make it a little bigger so you can see it more easily, and this is what we get. So, okay, so you can see that here's y equals x squared, which we saw a few minutes ago. If you add 2 to that, that 2, by the way, is the intercept. With a parabola like this, oh, I didn't realize I can't write on the tablet when I got it in this mode. Oh boy. Um, so I guess we'll have to get out of here. Unless look at that. I don't know why I didn't ask it to record what I'm saying, but it's doing it. All right. Yeah, let's get it. Yeah, never mind. We'll just leave it the way it is. I don't know what was happening there. I've never seen that before. Um, but anyway, so what we were saying is that y equals x squared and y equals x squared plus 2, the main difference between the two is the intercept. Okay, so in other words, so remember, the standard form for a quadratic equation is this. So clearly here, in this case, A is 1, B is 0, C is 0. This is the intercept. So this is the intercept is actually x equals 0 and y also equals 0 at that point. But when you're dealing with this one, by the way, I can use different colors here, which is kind of nice. So in this case, the intercept is 2, meaning that this is where it crosses the y-axis. So by adding that constant at the end here, it shifts the curve up by 2 units. And so the intercept is 2. So you can imagine if I shifted it down, it would look something like this. Let's go with green this time. Have a little meter. So this one is pretty straightforward. By adding a constant, or in this second case, you're actually subtracting a constant, you're just shifting the function up and down by a fixed number of units. And that's going to be true no matter what the function is. For example, if I had y equals x cubed, and then I want to look at, let's say, y equals x cubed plus 2, it's the same thing. It just gets shifted up by 2 units. The intercepts are 0, 0 and 0, 2. All right. But in what other ways can functions be transformed? Now, here, this one is a little bit tricky. If you notice, they've got the original parabola, y equals x squared, which again has the same intercept 0, 0. But surprisingly enough, if I add a 2 in the parentheses, it shifts the curve to the left. And you can see when x is negative 2, y will be 0. So it doesn't sound right, does it? No. But by adding that 2 inside the parentheses, the intercept is shifted to the left actually and becomes negative 2. And you can probably guess what's going to happen if I shift it to the right. This curve, oops, change that to a different color. Oh my God, it's actually disobeying. Okay, and that shifts it to the right. Wow. That was a little bit surprising, but this is what's happening. Okay. What other transformations might we run across? Well, we also, if you notice, again, they like to start with the y equals x squared. It's a good example. And this time what they're going to do is change the sign. Oh, let me do one thing here. Okay, so again, going back to the original function, if I multiply that by -1, it's not a perfect drawing, but I mean, it's supposed to be a mirror image from top to bottom. Maybe I can tighten that drawing up a little bit. All right, that's better. Okay. And again, you can kind of see why, because remember, as a rule of thumb, when you're looking at a quadratic equation, this is our intercept, which in both of these cases is 0, by the way. But this is what determines whether the parabola is facing up or down. So in other words, if A is positive, parabola faces up. And if it's negative, the parabola faces down. And that's exactly what we're seeing here. So there's a name for this type of thing. Sometimes it's called a reflection, but they're not using that terminology. Oh, yes, they are. It's right here, reflection, meaning up and down. It's almost like you're standing on, imagine yourself standing in front of a very still body of water, and you look in there, and what are you seeing? You're seeing the reverse of what you normally look like. Or if you were to hold up a diagram to that water, you'd see the reverse. So it's called a reflection. Now here they decided to get really carried away. They've done a couple of different things. They've added this 3 in here, which we know will shift the curve to the left, and then they made it negative. And then on top of that, they added a constant. So you got 3 things going on here. The +3 shifts it to the left, the negative flips it upside down, and that +1 shifts it up. So it ends up where you see it there. So they decided to get a little carried away there and do 3 things at once. All right, so they're combining everything we just did. All right, so this is just a summary of what we were just doing. This is a just a general list, and there is one here that they didn't actually get to. This one at the bottom, reflection about the origin. Um, Let me just show you an example of this. If you had, yeah, I'm not actually, maybe I don't want to. Let me just go to Symbol Lab and see if I can create an example of this. Well, we know what y equals x cubed looks like. So if we change that, what we're going to do here is, oops. All right, let's see how that turns out. No, that didn't work because it's the same thing. I think what, Yeah, that doesn't seem to have done the job. All right, I guess that's not a good example. So the idea is that it's supposed to go, in other words, wherever you had the first and third quadrant, it's supposed to flip it over to the second and the fourth quadrant. I guess this was not a good example. I'll think of one later on and we'll take a look at it. But right now I can't think of any good examples. Um, Now here they're going to classify functions. And for the most part, I mean, we're familiar with all of these algebraic functions. There's many different kinds that we've seen: polynomials, radical functions, rational. And they'll discuss these again as we go along. Trig functions, again, you're very familiar with those, sines, cosines, et cetera, et cetera. And then finally, exponential and logarithmic functions, which again, you've seen in pre-calc. So what they're going to do is remind us what a polynomial is all about. And so it's a very general expression. You have all these terms, and you notice what's happening here is that the exponents themselves, these n's, are required to be non-negative integers. And of course, we already know that non-negative means zero or positive, right? If any of these exponents are not integers or they're negative, then this does not qualify as a polynomial, right? It has to have only integers. And you can see the x's have progressively smaller exponents. That's just a general expression for a polynomial. So they're writing it in the most general possible terms. And then the last couple are going to be a2, x squared, a1x, and then a0. So the ones that we're most familiar with, and by the way, the value of n determines what's called the degree of the polynomial. All right, so in other words, if I have a cubic equation, and then they'll call it either degree, or sometimes you hear it called order 3, because the highest exponent is 3. Okay, that's one of the ones we're very familiar with. You could also have, for example, a quadratic equation. And then, of course, we're very familiar with the linear equation. And these, again, are all types of polynomials. And then you could also have a constant function. Order equals 0. Okay. Or actually, let me be consistent here, a constant equation or function. And that is defined to have an order of 0. Okay, so the orders are always integers and they're never negative. They've got to be non-negative. And they can go higher, you can go as high as you want, but in principle, I mean, when you're thinking about real world applications, these are the ones you normally encounter in practice. It's rare to run into higher order polynomials than these. Very rare. Okay, so oh, and one more thing, the coefficient of the highest order term, this is defined as what we're going to call the leading coefficient. And the reason why they're bringing that up is because sometimes that number will be needed for whatever solution we're looking for. Depends on what exactly we're trying to do. And I guess here there's only one coefficient, so it gets to be the leading coefficient. Okay, great. So those are our best known examples of polynomials. Um, the A's themselves can be zeros, except for the leading coefficient. That one can't be a zero, but the others can. So in other words, if I just have up here y equals x cubed, that would fall into this first category, but that would mean that A2, 1, and 0 are all just zeros. Okay, so the only one that can't be a zero is the leading coefficient. All right, so this is what we were just doing, except they're using letters A, B, C. Now, there are certain properties. Once you start to get comfortable with these polynomials, it turns out the behavior of their graphs will depend on whether the order is odd or even. Okay, in other words, cubic equations, fifth order equations, and higher, they will have certain properties that the even ordered ones like 2 and 4 do not have. Specifically, the even ones, um, let's see. So these are the even cases. In other words, it could be a quadratic equation. Um, Actually, I think when we get up to order 4, I think the name changes to quartic equation. There's a chart in Wikipedia somewhere um, where we can look this up. Surprisingly enough, you wouldn't think so, but Wikipedia actually has a lot of excellent content with respect to math. This is one area where they're actually pretty good. And some areas, who knows? But here they really do a pretty good job. So let's see what we can find. Maybe not this one. All right, let's try that again. Um, Here we go. This is what I was looking for. I guess I just chose the wrong search terms. So zero, linear, quadratic, cubic. Here we go. This is what I was thinking of. Um, Quartic is the fourth order polynomial. Quintic is fifth. Now, these are getting to some very strange names. These are things you don't hear every day. These are all, of course, taken from Latin. This is where they come from. Quintic is 5. Sextic is 6. Or hexic. You've heard of hexagons. They have 6 sides. Septic is 7, or heptic. Octic is 8. Nonic is 9. And decic is 10. Um, yeah, so it's all from the Latin. Basically, everything in math is either taken from Latin or Greek. Usually, now the Greeks were really good at geometry, so terms in geometry tend to be Greek words. The Romans were more interested in algebra, and so we tend to run into Roman terms, or Latin terms, I should say, when we're dealing with algebra. But you never know. Along the way, other languages got sneaked in there too. But anyway, let's see. So yes, so what they're getting at here is that they're showing you how, if as long as these are even order polynomials, if the leading coefficient is positive, you're going to get behavior like this one on the left. If it's negative, it'll be like this one. Now, the quadratic functions are special cases of this, as we were just discussing a little while ago. So remember the way this works, this is, so A2 is the leading coefficient. So here A2 is 1. Or if you're just using the more, this is just the special case of a second order polynomial, but remember we sometimes see it written like this. This is the more common way of expressing a parabola. So the rule would then be if A is positive, the parabola faces up. As you can see that that's the case. A is negative, it's the other way around. Now, of course, remember, it can't be zero itself because that would mean it's no longer a quadratic equation. But the sign is going to tell us. So when you get to the higher order ones, like a to the fourth, x at fourth order, then the behavior gets a little bit more complicated. But the basic result is that it falls and then it rises. If the leading coefficient is positive, if the leading coefficient is negative, it rises and then it falls. So we go back to symbol lab. Let's take a look at what y equals x to the fourth really looks like. Okay, so it's kind of like a steeper version of x squared, except it's kind of got this flat region at the bottom. And of course, if I make it negative, it'll just be upside down. But again, the point of this is that it does fall and then it rises when a leading coefficient is positive, and here it's going to do the opposite. So if we had other terms in between, you get more complicated behavior. Let me just make one up at random and see what happens. Yeah, I mean, the bottom, it looks a little strange, but it does have that same basic property. It falls for a while, and then after that, it rises, and it continues to rise forever. If I were to make all these terms negative of what they are now, it would just flip the whole thing upside down. Now, this is for even polynomials with an even order or degree. What about odd? Well, odd changes everything because you know how odd, like the cubic equation, rises and then it tends to dip and then it rises again. So if we have an odd degree, like 3 or 5, let's say, then the function rises and falls and rises, but in a somewhat different way than it would for the even degree functions. Okay, so let's say you have, and I think we may as well use examples we had earlier. We'll try x cubed and negative x cubed. Yeah, so it rises and it sort of levels off a bit and then it continues to rise forever. And then if I make this negative, it'll just flip the whole thing upside down. And that means that it's falling, flattening out, and then falling again. Okay. In other words, the way to think about this is that, at least in this case, there's no point where the function is rising. It's falling. It's the rate at which it falls is changing, but it never starts to dip up again. Now, if we added more new terms, it's still going to start to look a little different, but the basic shape won't change. Yeah, see, now this time it starts to dip down, but then it curves back up again. So that's because of these terms in the middle. But again, it rises, then that rising is interrupted for a bit, and then it just continues to rise forever. All right, now rational, now with this word rational, it contains the word ratio, and there's a good reason for that. So if we have a function which is itself a ratio of two polynomials, then we call it rational. The only constraint here, of course, is that the denominator can't be zero. Now, polynomials and rational functions are types of algebraic functions. They're clearly not logarithms. They're not exponentials. They're not, also not trig functions. But we have this other classification. Algebraic functions must contain a finite number of terms. It can have any operation we choose, sums, differences, multiples, quotients, radicals, but anything that doesn't fall into that category can be defined as transcendental. Now, I don't know how important that really is, but a function like y equals e to the x is considered to be transcendental because the number of digits in e goes on forever without repeating. So here, now here they're showing you different ways you can combine functions. They're very straightforward. You can add them directly, you can subtract them, you can multiply them out, you can divide. But the one thing that we did see this in pre-calculus, but it's something that still takes a little getting used to, is the idea of composite functions, where one function is a function of another. So we often see it written as f of g of x, or sometimes you write it like this. And so basically, it's a two-step process. We have the inner function. G of x is the so-called inner function. And f is the outer function. And by the way, not that we're going to do this here, but there's nothing to stop us from having more than one inner function. We can have as many functions as we want, but here we'll stick with two. So, all right, here's a good example. Let's try this. Let's make sure we understand how this works. My computer's being very stubborn. There we go. Oh, why did I write that word? I wanted to write composite. I was thinking about how stubborn my computer was. So we often write it as f of g of x. Sometimes you see it written like this. It's a shorthand. And so the ones they're giving us are 2x minus 3 and x squared plus 1. So how do I find f of g of x? All right, in order to do this, I want to remind you, let's take a bit of a detour here. Suppose I was trying to find f of 3. What would I do? I would go through the equation and replace all the x's with a 3. So this is exactly the same thing. Replace all the x's with g of x. So in other words, I'm going to write this as 2g of x minus 3. Okay, now I'm going to substitute what the definition of g of x into that equation. Remember, we defined g of x to be x squared plus 1. Now I just do a little algebra. I distribute this 2 across both of those terms. 2x squared plus 2 minus 3. Okay, and we're done. Now I can also solve for g of f of x. I can let f be the inner function now. So let me do one thing here. G of x is x squared plus 1. F of x is 2x minus 3. All right, so this time what I'm going to do is take g of x and replace all the x's with f of x. Okay? Now I'll substitute the function here. And I guess you could leave it like this, but if you wanted to expand it, you can multiply these together. You could use the FOIL technique here. F would be these two terms. Outer is negative 6x, as is inner. And then last is these two, a positive 9. And now all of that gets put in here as a replacement for 2x minus 3 squared. Don't forget about that 1. It would be the easiest thing in the world to forget about it. So it's 4x squared minus 12x plus 9 plus 1. And that's your final result. Wow. um, by the way, I want to mention, we don't have to do it right now, but when it comes to composite functions, we could also define f of x if we wanted to, and we could have g of x, a composite function with itself. You would have follow the same steps, okay? All right, now they want us to think about the zeros of a function. Now, what does that mean? Well, the word zeros the zeros of a function are the values of x at which y equals 0. Okay. Graphically, these are the points where the graph crosses the horizontal axis. So imagine you have this parabola. All right, so I'm going to quickly make up an example on a piece of paper over here. X squared plus x minus 6. So I want to know where those points are, where the function crosses the axis. So what I can do is first factor this out. And then I'm going to set it equal to 0. And what this tells me is that the product here equals 0, but that means each individual term also equals 0. Because if one of them becomes 0, the product equals 0. So that means I actually have two things going on here. Those are my solutions. And that means that this point here is negative 3, 0, and this point is 2, 0. And that's what I mean by zeros. And sometimes they're also called solutions or roots. of the function. Okay. Now, of course, the number of solutions depends on the degree of the polynomial. Um, a linear function have only one solution. A cubic function, depending on which one it is, can have up to three solutions. Okay, so in other words, a linear function would look like this. A cubic, if it crosses through, like this one, has three solutions. And so the number of solutions depends on the degree of the polynomial. By the way, just as a side note, when it comes to the quadratic equations, here's something that you might not have realized. If you have this parabola, guess what happens when I set this equal to 0? Oh my God. The solutions or zeros or roots are both imaginary numbers. Now that will happen if the parabola never quite crosses the horizontal axis. So this is a very strange case because there are two solutions, but they're both imaginary. In these cases, they're all real, of course. So you're going to get this with some types of situations. Now, I don't know how much time we're going to actually spend with imaginary numbers in this course. It's not going to be very much, but there was some discussion about this in pre-calc. Just remember that, negative 1, square root negative 1 is I. This is an imaginary number. It's thought to exist in a different dimension, basically, than the real numbers. And then when you have something like this, we call it a complex number because it has both real and imaginary components. Now, complex numbers can be very important. There are areas in which they run into them. You wouldn't think so, but like engineering applications and some very advanced statistical applications, you might actually run into them. Now, if you're in the math department, way down the road when you're getting to be, let's say, a senior, they sometimes offer an entire course in just what's called complex analysis, which does nothing but look at complex numbers. So it is a very important branch of mathematics. It's just that we don't really need it very much right here in Calc 1. But anyway, so now here's another interesting set of concepts. Sometimes functions can fall into one of two categories, which are called even and odd. Now, it turns out most functions don't actually fall into either category, but how do we know the difference between the two? Even means actually, no. Okay, so like a perfect example of this is, so if let's say if x is 3, y is 9, if x is negative 3, y is also 9. Okay. So in other words, because of the way the graph is drawn, you can see that for every positive x, the corresponding negative x will have the same y value. Or in terms of geometry, you can think of it as being symmetrical with respect to that vertical axis. Okay, so this is what it means to be an even function. Now, odd means so in other words, the classic example of this is y equals x cubed, which means that if x is 2, y is 8. If x is -2, y will be -8. And that'll be true for all x's. Okay. So here, there is symmetry, but it's not with respect to the vertical axis. It's with respect to the origin. Okay, in other words, the first and the third quadrants in this case are identical to each other. Or I should say mirror images of each other. So here there's symmetry. And here f of x is symmetrical with respect to the origin. In other words, across like between the first and the third quadrants, or possibly the second and the fourth quadrants. So, or, algebraically, f of x equals f of negative x, as I wrote here. And f of x here equals negative f of negative x. Now here they want us to double check this one, x cubed minus x. Now you can try specific values of x, but in order to prove that it's either odd or even, it must be true that this result is the same for all x's. So odd would indicate this. So here's what we're going to do. We're going to solve for f of negative x by replacing all the x's with negative x. And that means we have negative x cubed plus x. So that means that negative f of negative x equals positive x cubed minus x, and that equals the original function f of x. So this equals this, and we have our proof that this is an odd function. Now you can try specific values if you want. Another thing we might as well do is have SimpleLab show us a graph of this so we can visualize what it looks like. X cubed minus x. And remember, it's supposed to be symmetrical with respect to the origin. And there it is. You can see that the first and the third quadrants are mirror images of each other. All right. Now, here's an interesting one. 1 over x squared. They want to know if it's even, odd, or neither. Well, the fact that there's an x squared in here means that if it is one or the other, it's going to be even. Okay, that's one way. So we're not going to bother testing it for odd, because we know it's not odd. So we want to know what is the value of g of negative x. So they're equal to each other. Oh, oops, g of negative x. And that implies that g of x is an even function. Okay, so that's that. That was an easy proof. You can see the symmetry from left to right. Ooh, now here's a tricky one. Negative x squared minus x minus 1. So let's start by checking it to see if it's even. If it is, then this statement is true. So let's find each of negative x. So what am I doing again? I'm replacing all the x's with negative x's to see what happens. So you can see they're not equal to each other. So let's see, just to be consistent, to be complete, or we want to see if it might be odd. Well, let's see. Now we already just got through showing that h of negative x is negative x squared plus x plus 1, which means that negative h of negative x is positive x squared minus x plus 1. Is this equal to the original function? It is not. Okay, so h of x does not equal. So therefore, h of x is not odd either. And it's just neither, right? A lot of functions are neither. All right, it's not that unusual. Okay. So that's section 3 of the preliminary notes. So part 4, remember I did mention, is our review of trigonometry. Now, it looks like we're not going to be done in this hour with the trigonometry, but we can at least get started with it. So probably, I'm sure we can finish it in the next session. And once that's done, we can start the new material in chapter 1, which I'm sure you're dying to see. But we need to do this too, because it'll be a problem later on if you start to forget how trig functions work. So we're going to start at the beginning by reminding ourselves, what is an angle? I mean, really, that's kind of an important question. Now, also, I want to remind everyone that we often see the Greek letter theta used to represent angles. So there's an assumption. Oh, and one more thing, I want to remind you that if you remember, a line in geometry goes on forever in both directions. But a line that has a specific starting point and then it goes on forever is often called a ray. Okay, so here's a line and here's a ray. It has a specific starting point here. So the point where two rays join together is what we're considering. This point where they touch is called a vertex. So the angle between them, think of it as the rotation that it takes to go from the initial ray to the terminal ray. And you'll also remember that we're thinking in terms of circles. And a circle, as you know, has 360 degrees. Oh, what a terrible drawing. And just while we're on this subject, a triangle has 180 total degrees in it. This one particularly is a right triangle, and that's because this is 90 degrees. But the entire circle is 360 degrees. So if you go around and come back where you started from, that means you've moved 360 degrees. So this angle is the proportion of the total circle that we've had to travel. So if that, for example, represents 1/4 of the total distance, then it must be 90 degrees. Okay, so that's how we have to think about it. The angle theta is the proportion of the circle that we've traveled to go from the initial ray to the terminal ray. You might remember too, we're going to discuss this in a few minutes. Angles can be measured as degrees or radians. Yes. Now, by the way, I do want to mention before we go any further that a lot of what we're about to do, you can get some help from your calculator. It has everything you need if you know how to use it. In particular, it can do radians and it can do degrees, but you have to know how to set it up properly. So, but we'll do these as we go along. The standard position. Now we're going to basically assume now, you notice here, the rays could have been anywhere in space. Here, we're going to assume that we're on the horizontal axis. We start on the horizontal axis and then we move from there. Okay, just to keep things simple. Okay, we call this the standard position. And so here's theta, meaning how far did we travel from the horizontal axis to get to the terminal ray? Theta is the angle. In this case, we're talking about degrees. And there are names associated with these different angles. You might remember angles below 90 are said to be acute. Between 90 and 180, they're said to be obtuse. And there's other names as well, but these are the important ones. By the way, here's a fun fact you might have forgotten about. When we describe degrees, angles in degrees, it's understood that we're moving in a counterclockwise direction. Okay, in other words, let's go get a picture. Let's say that now, oh, by the way, I also want to remind you that since the entire circle has 360 degrees, the distance from one quadrant to the next is 90 degrees. So let's say this is 135 degrees. In other words, I had to go through the entire first quadrant and then halfway into the second quadrant. So this, in other words, this piece by itself is 90. This is 45. Let me move this out here. The total is 135. Angles are measured in a counterclockwise direction. What if we go the other way, though? Well, we're at the same terminal ray, so this angle actually is the same angle, whatever this number is. You notice how, in order to get here, we had to go through the entire fourth quadrant, third quadrant, and halfway into the second quadrant. These add up to 225 degrees. But because we're going in a clockwise direction, this is defined as a negative angle. So in other words, positive 135 degrees and negative 225 are the same angle because they bring us to the same location. So we sometimes say that 135 and negative 225 are coterminal angles since they share same. They have terminal side. Okay. In other words, they bring us to the same point. It must be the same angle in some important way. So we have negative angles if we're moving clockwise, positive if we're going negative counterclockwise. So that's the convention that we'll follow. Otherwise, there would be chaos. Imagine if we left it like this without the negative, that would indicate that 135 and 225 are the same angle. Well, they're not. So we have to call it something else. So we're going to call it negative 225 to indicate that we're going in a different direction. So notice in this example, they went halfway down into the fourth quadrant. Actually, let me draw the whole circle so you can see it better. So it's negative, it's halfway into this fourth quadrant. Half of 90 is 45. So the negative angle is 45. The positive version, which requires us to go all the way around the circle in the other direction, let me change the color. Ninety, 90, 90, and 45, which adds up to negative, a positive 315. So in other words, the sign depends on what direction you're going in. So the 315 is the positive angle because we're going counterclockwise. The 45 is the negative because we're going clockwise. But they do bring us to the same location, or terminal side as it's called. So they're both said to be coterminal. Now, if you find this confusing, there's a little trick you can follow. When you have a situation like this, the absolute values have to add up to 360. So that might help you remember how to figure out what angles are coterminal with each other. Just make sure that the negative and the positive one in absolute terms add up to 360, and then you'll be all set. Now, sometimes we might go around the circle more than once. What do you do then? All right. Oops. And you went all the way around and then another. Oh, wow. I didn't ask it to do that. Look at that. I don't know why it did that. It said, listen, that's not a nice circle. Let me straighten it out for you. But I want, we need to then go up here, let's say, another 45 degrees. So a round circle plus another 45 degrees is officially considered to be 405 degrees. But 405 and 45 are the same thing, because it just means in one case you went all the way around. And then it's like, imagine you got lost. You drove past the house you were looking for. You go all the way on the block and you come back and say, oh, there it is. I missed it the first time. That's what's happened here. So those are also said to be coterminal. All right. And it goes in, if you go back, go to the left, it's the same thing. All right, we're gonna have to stop here because now we have to remind ourselves how radians work. And this is a fairly complicated discussion. And it's something that, I don't know, I find people find radians to be very confusing. So we'll save this for our next session. And yeah, it's time to stop here, but so we'll pick it up with our discussion about radians, and then I'll show you how the calculator can help us find what we're looking for. It can do either radians or degrees, but you have to know how to set it up properly. So we'll have to stop right here. And when we come back, we'll discuss radians, and then we'll also reintroduce all the basic trig functions. So that we have that to look forward to next time we meet. All right, so I guess I'll see you next time.